Hello, and today I am going to talk about black holes, what they are, how do they form, and probably most interesting, what happens if you fall into them. So the black hole that you're currently looking at right now, probably there, is the black hole from the movie Interstellar. And irrespective of the rest of the movie, the black hole itself and the visualizations of the black hole were really amazing. So much so that the graphics department that made that movie spun off a whole nother section of the company in order to deal with simulations with general relativity. So let's start off with what is a black hole anyways. And the short answer is an object so dense that light itself cannot escape. But the long answer, what does that really mean? So every object that has mass has a gravitational field that pulls everything towards it. In order to escape, you have to have a certain escape velocity. So you need to be going a certain speed in order to be able to get out of that gravitational pull. So here we have an equation that shows how fast you need to be going. So it's the square root of 2 times some constant times the mass of the object divided by the radius of the object. So I can take this equation and solve for some boring examples. So the asteroid Bennu, from which we collected samples and in order to figure out what asteroids were made out of, has an escape velocity of 0.2 meters per second because it is relatively small and relatively light. This means that a slow turtle could not escape. So we could call the asteroid Bennu a turtle hole. Phobos, which is one of the 2 moons of Mars, has an escape velocity of 11.4 meters per second, which is about how fast the fastest sprinters could run. So it's a little bit faster than that. So Usain Bolt could not escape this moon on a sprint. So we could call this a human hole. The Earth has an escape velocity of 11,200 meters per second, which is blazing fast. So fast that our rockets can escape, but it takes a lot of effort to get a relatively small mass outside of Earth's gravitational pull. So the Earth is almost a rocket hole. But luckily, we're just barely light enough, we're just small enough that we can in fact get out and explore space. If you pack enough stuff inside a small enough radius, the speed that you need keeps going up. The fastest anything in the entire universe can go is the speed of light, which is 3 times 10 to the 8th meters per second. Translated, that's 300 billion meters every second. For those of you that prefer miles, this is 670 billion miles every hour. Or, if you prefer small numbers, 1 foot every billionth of a second. So, the first uncomfortable question that we're going to talk about is, Mommy, where do black holes come from? And the short answer is dead stars, which brings us to the second uncomfortable question, which is, Mommy, where do stars go when they die? And it all depends on size. So for those of you who haven't seen this video that's right above my head, I'm going to supply a link to it, and it shows just how giant the things in the universe are. For instance, our sun is one of these really, really small ones, like right above my finger. And these stars get way, way, way bigger. So stellar evolution is a long topic in and of itself, but we'll give you the short version today. So small stars like ours burn through the hydrogen at its core. It's not really burning, it's nuclear fusion, but we'll take some liberties with language. And Once we're done burning through the hydrogen at our core, we're going to start burning the helium at our core. And this is going to cause our star to puff up and become a big fluffy giant. In fact, our star will get so big, it's going to be the size of our current orbit, which might mean that Earth will get swallowed by our sun, or we might just drift just far enough that we're not going to get eaten. Either way, we're going to be turned into a crispy charcoal briquette, so we're dead either way. Good news, it's not going to happen for another 4 billion years, so something else is going to kill us first. And then our sun will fuse all the way to carbon. It will fluff out its outer atmosphere, but it's going to hold on to its core. And it's going to end its life as a white dwarf. It's essentially going to be a giant diamond. And I did some math here. It would be 2 followed by 33 zeros carat diamond. Yeah, you can make a lot of money with that if you have a time machine. So what happens if you have bigger stars? Stellar evolution is all about the balance between gravity pulling in and other forces pushing out. While a star is actively fusing stuff in its core, the gravity's pulling in and light is pushing out. When our star dies, gravity keeps pulling in, it still has the same mass, and the electrons in all of those carbon atoms are going to be repelling each other so that it doesn't all collapse. Bigger stars have more mass, therefore more gravity, and electric repulsion is not going to be nearly enough. Also, with these bigger stars, you end up with denser cores because they are able to fuse all the way to iron and therefore have much more massive atoms forming their core. So this is where neutron stars come from. When a star has about 1.4 times the mass of our sun, when the fuel runs out, the stars collapse. And massive amounts of runaway fusion happen in the core. Lots of heavier elements produced. For instance, the gold ring that you may be wearing right now was probably forged in the heart of a supernova. And this leads to a gigantic explosion, several times brighter than the galaxy that it's in. And this is the supernova that I mentioned just a little bit ago, spoiling my punchline. So what is left is that neutron star, if it's just the right size. Gravity is so strong that the electrons can no longer repulse the atoms away. Everything condenses down to neutrons. You probably have heard that an atom is mostly empty space. If I had a nucleus about this size, the nearest electron wouldn't be for about 10 miles that way. And something that is more massive than our sun collapses to be about the same size of Manhattan. And the thing that keeps the star from compressing anymore is something called neutron degeneracy pressure. Trust me, you don't want to get into that. It'll make your head hurt. But if it's even bigger than that, you will get a small black hole. At about 3.5 solar masses, the neutron degeneracy pressure can't keep it all apart, and it compresses down into a black hole. And nothing that we know of can keep matter apart under those forces, which might mean that it shrinks down to something that is infinitesimally small. It could become infinitely dense, or there could be some new state of matter that we don't understand yet, and so it could have a volume that's inside, just it's really small. The really important bit for a black hole at this point is that we have a mass that's really, really large and a radius that's small enough that light isn't getting out. So anything beyond this point is just an educated guess. And we have a really good education. We can make really accurate guesses. But this also provides a spot for science fiction writers and other kooks to make stuff up. And by other kooks, I mean folks with PhDs in physics that want to try to imagine what happens in the middle, but we really don't have a way to test those, at least not yet. So the takeaway that I want everyone to have from this is a black hole is just another object that's dense enough that light, and therefore everything else, cannot escape. The light instead would go into orbit around the center of the black hole. They are not, and black holes are not the giant vacuum cleaners that you see in movies. So this picture is from the reboot of Star Trek, and you have this red matter that can turn planets into black holes, and then they suck away all of Starfleet's ships. That's not what happens. If the Earth were to become a black hole, it would be about this big. It would be about the size of a marble. Our moon would happily keep orbiting because all it cared about is, hey, look, there's an object that has a bunch of mass right there. I will be in orbit around it because I can't escape. And so this is actually how we are able to find black holes in our galaxy, is we can look at other stars and we can find stars that are orbiting something that we can't see. So this brings me to Andrea Getz, and she's my hero. So she discovered the supermassive black hole at the center of our Milky Way. And she also, in reading about her work, is what sort of inspired me to go, hey, look, maybe I can do this physics thing after all and learn cool things. And she then won the Nobel Prize in Physics in 2020 for discovering that supermassive black hole, which is just plain cool. So this is, what's playing above my head is the pictures that she took, the movie that she essentially took of the center of our galaxy. So she photographed this using a whole bunch of fancy telescopes over in Hawaii, infrared telescopes, using adaptive optics, and she then saw stars orbiting this invisible object right there in the middle. And you can actually do all the math for these stars that are above my head. The one that's whipping around the center is called S2, and it's nasty math, but you can do it and figure out that this black hole at the center of our galaxy is 4.1 million times the mass of our sun. So, the other neat thing is that black holes ain't so black. And this is a quote from Stephen Hawking, so you English teachers, don't yell at me for my grammar. So, for something so massive, black holes are really, really small. And things fall towards them and get caught up in this disk and essentially it gets trapped in orbit around the black hole. And the best analogy that I've got is imagine a bathtub full of water. If you pull the plug out of the drain, all the water is eventually going to drain out, but it takes a while, and you end up with this gyre, that whirlpool that sits there as it slowly sucks everything down the drain. Something similar is happening with a black hole. And so you end up with an area where you have a whole bunch of stuff that's really high energy, smashing into other things that are really high energy, so you can have nuclear fusion happen inside this accretion disk. And that means that fusion can happen without the rest of the star getting in the way. So some of these black holes can be the most energetic things in the galaxy, and some of the most energetic things in the entire universe. They can actually be the brightest objects. So almost all galaxies have a supermassive black hole in their center. This is one of those things where with the James Webb and the Hubble before it, everywhere we look, all the galaxies except for ones that we can explain because of interactions with other galaxies, have this supermassive black hole in the middle. We're not 100% sure why yet, though. And so how they form is still a mystery. it's not that we don't know, it's that we have lots and lots of good ideas and we don't know which one is correct. So this galaxy above me is Centaurus A, and it has plasma jets extending over 1 million light years. So it would take 2 million years for light to get from one end of this galaxy jet to the other, which is beyond mind-boggling. So we are really lucky that the supermassive black hole in the center of our galaxy isn't hungry. Well, not to anthropomorphize it too much. It's just nothing's going to be falling in for the foreseeable future, which is really good, because if it were to be actively feeding, like this one in Centaurus A, the radiation could be strong enough that it could wipe out life in the entire galaxy, which would be bad for our life expectancy. So, speaking of which, let's talk about what happens if you were to fall into a black hole. So, the first thing that we should probably talk about is its gravity. And gravity causes things to accelerate. And we know this because I could take this capacitor and drop it, and it is going to get faster and faster and faster as it goes all the way to the ground. The closer you are to the black hole, the faster you accelerate. So eventually your feet are going to be trying to accelerate way quicker than your head, and the difference in that acceleration is eventually going to be big enough that the molecules in your body aren't going to be strong enough to keep you together. And this is what we call spaghettification. Sometimes in science, we come up with cool names. It's rare, but sometimes. Basically, you get drawn out like one big thing of silly putty. So let's say that you are a proper Highlander. You are immortal, and spaghettification for you just means this strange Italian dish that some Spaniard named Sean Connery brought you. Yeah, we'll go with it. So inside the short shield radius, which is just the fancy vocab term for that radius from which light can't escape, all the light that falls in is now in orbit. So everything that gets eaten by the black hole might just stay in orbit inside that radius, which means that if you were to fall through that radius, you are now burnt to a cinder. Ouch. And even if you aren't burnt to a cinder, you still can't escape. So that's the end of you. There's a whole bunch of wishful thinking when it comes to sci-fi in that, hey, look, the math might tell us that the same black hole could exist at different spots in the space-time continuum, and that would form a wormhole. All right, maybe. The math says that might happen, so it might happen. But you still ain't getting out the far end. So some caveats before you then fill up my inbox with a whole bunch of questions. Well, everything that I said was true. This is all still the simplified version. So most physicists never bother studying general relativity. It's only the astrophysicists that would end up using it and the cosmologists that really study it. And this is very, very hard. So hard that most of us don't bother. It took Einstein 10 years to figure out general relativity. You can spend your entire career studying black holes, and this was just the tip of a very, very deep and massive iceberg. After all, this was only about 45 minutes. Tensor calculus, which is what you need to understand all this, makes your brain hurt. After all, it looks like that. So with that, I hope you enjoyed it, and I hope that you can join me for the next one, which will be about dark matter. All right, now I have to figure out where the stop button is.